Welcome to the third part of magnetism. As per custom, we have looked at simple phenomenon of magnetism. We have also looked at electromagnetic effect. In this video, we're going to take a look at AC generators. Then in the next and last video, we're going to take a look at transformers. So we're going to start a simple AC generator. First and foremost, AC stands for alternate current. Alternate current is a type of current which changes direction many times per second. The opposite of AC current is called DC current, which is direct current, and direct current doesn't change directions per second. Okay, in simple ways, direct current has one direction, while alternate current can have different directions. It can go back and forth. In layman's ways, we can say AC current is the current from Z-score, while DC current is the current that we can get when connect a circuit to a battery or a solar panel. Okay, so just know that DC, which is direct current, doesn't change direction many times per second, while AC current changes direction many times per second. So AC generators basically generate alternate current by electromagnetic induction. So in the previous lesson, where we talked about electromagnetic induction, we talked about Faraday's law, we talked about Lenz's law. So the concept of electromagnetic induction is centered on a magnet that has a magnetic field around it and a wire. So we said that when a wire is moving across the magnetic field, current is introduced in that wire. Okay, that's what we said. So I want you to see this in two ways. The first is a situation where we have a stationary magnet and a wire that is moving. So we have a stationary magnet, means that the magnetic field is stationary, it's not moving, well the wire is moving. So as the wire is moving, it is cutting across the magnetic field, and in the process current can be induced. The other situation is where the wire is not moving and then we're moving the magnetic field. So if this magnetic field is being moved, it means if this magnet is being moved, it means the magnetic field is also moving. Therefore the magnetic field is being cut by the wire, and therefore current can be induced. So these are the two concepts that I want us to have in mind as we are studying AC generators and the next topic, transformers. So for AC generators, the core concept is a situation where the magnet is just here, it's stationary, meaning that the magnetic field is also stationary. So if the magnetic field is stationary, we are going to have wires moving, and because the wires are moving, current is going to be induced in the wire. And remember, like I said last time, that's how electricity is made. So this is a simple AC genset. This diagram just portrays a simple AC generator. So what we have is a magnet and a magnet. So there will be a field here. Okay, since there is a field here, then there's going to be a coil. So this coil is not going to be like a solenoid which is like circular. So this coil, the way it is square like this. Okay, so this coil is connected to some circuit. So this coil will come here and it's coming here. So this coil is connected to this circuit here. Okay, so the connection between the coil and the circuit is made of these part which are called carbon brushes. So this is a carbon brush and this is a carbon brush, and then we have these ones which are called split rings. So the way the split rings are connected is such that this line connects to one split ring and this other line or wire connects to the other split ring. So what's going to happen is this is going to be rotating. As this is rotating, the split rings are going to also be rotating. But as they are rotating also, the split rings, they are going to be in continuous contact with the brushes, and the brushes are the ones that are connected to this external circuit here. So the connection between this external circuit and this coil is going to be there even if the coil is going to be rotating. Okay, so I've talked about rotation. Where does rotation come from? So this coil has to rotate. The rotation is the one that is going to cause electricity to be induced. How? Because when this is rotating, the way to view it is, if this, let's say, it moves up and this moves down, it means a wire is moving across the magnetic field. Since the wire is moving across the magnetic field, then current is going to be induced in that wire. So that current now will be circulating in this circuit. So wherever the current is going to be induced, it's going to come here just like that. So if you have anything that uses electricity here, then you're going to make use of electricity. So one thing to note is this rotation now, where does it come from? What rotates the coil? So there must be an external force that rotates the coil. In wind generated electricity or wind powered electricity, it's the wind that rotates the coil. So this coil is going to be connected to something that's going to be rotated by the wind. So as it is rotating, the coil is also going to be rotating. As the coil is rotating, the wires are cutting across the magnetic field. And since the wires are cutting across the magnetic field, then according to magnetic induction, current or EMF is going to be induced in these wires. And that induction and that current or EMF that has been inducted is the one that we're going to use as electricity. So this is how electricity is made, and this is how AC generators work. So in Zambia, for example, at Kariba, the moving water, as it is passing, it rotates the turbines. So the turbines, as they are rotating, they end up rotating the coil. So as the coil is rotating, then the induction happens and we have power. So I've given you just a general view, but what is it that you should take for the syllabus, for what is expected of you during exams? So you have to know the role of each of the parts of this simple AC generator. The first is the coil. What's the function of the coil? The coil is the one that actually produces electricity by electromagnetic induction as it is rotating. Then what about permanent magnets? Permanent magnets are there, of course, to produce the magnetic field. Next, we talk about carbon brushes. So the carbon brushes keep the contact with the rings continuously. So these carbon brushes, they make sure that they keep the contact with these rings continuously. What about the same slip rings? So the function of the slip rings, of course, the slip rings are fixed to the coil. So this is one of the points I'd emphasize on. These slip rings are fixed to the wires of the coil, and they make sure that, which is their function, they make sure that the coil is always connected to the outer circuit. So their job is to make sure that the coil is connected to the outer circuit, and the job of the carbon brushes is to make sure that they are in close contact with the slip rings. So that's how these are the functions of the. Now there are two types of rings that can be used here. There are these slip rings, and there are also what are called split rings commutators. So split rings commutators are these. I'm sure some of us have seen this somewhere. So these are called split rings commutators. The difference between split rings commutators and slip rings is slip rings they are like cylindrical. They are cylindrical. They don't have cuts or splits. Well, these ones are splits of, like they are not full cylinders. They are parts of the cylinders. So in between them there is space. Well, the slip rings, there's no space. It's just one thing. Well, split rings, there is space between these ones. the cylindrical part. Hope you have gotten the difference. Slip rings is just one cylindrical thing. Split rings, they have split, they are split, they have spaces in between. Okay, so when the slip rings are replaced by split rings, then what we're going to produce is DC current, not AC current. Okay, so slip rings is for AC currents, split rings are for DC current. So what you should get is slip rings are for AC, split rings are for DC. So they are usually used to, the split rings are usually used in DC generators, not AC generators, since AC generators are for slip. So this diagram explains the relationship between induced current and direction of rotation of the coil. So when the coil is like this, when it is perpendicular to the direction of the field, so the field has, usually in that arrangement of magnets, has to be from left to right or from right to left. So when the coil is at 90 degrees, so if the field is like this, it means the coil is at 90 degrees. So when the coil is at 90 degrees, there is no current induced, so current is 0. So as the coil starts moving, rotating clockwise, then the amount of current that's going to be induced will start increasing. When it reaches like this, then the amount of current induced is going to be at maximum. Okay, again, when it continues rotating clockwise, the amount of current is going to start reducing. Then again, when it reaches like this, when it has rotated about 180 degrees from its initial position, then the induced current is going to be 0. Again, when it continues rotating, the induced current is going to be increasing, but it's going to be negative. Okay, so it's going to be negative, and when it reaches like this, then it's going to be at maximum, but with a negative value. Okay, then again, if it continues trying to go back to this position here, it will start increasing towards the positive or towards 0 till it reaches 0. It's like this. So these sequences 1 2 3 4 5 keep on happening and will produce this kind of a wave. So the frequency of this wave is proportional or is equal to the number of rotations of the coil per second. So if the coil rotates 20 times per second, then the frequency of this is going to be 20 Hz. Okay, so in short, if you have been given the frequency of the wave that is being produced, you can tell the number of rotations. If the frequency is 50 Hz, then the number of rotations of the coil is 50 rotations per second. So that's the relationship between the frequency of the wave that's going to be produced and also the number of rotations of the coil. So now to increase the induced EMF or current, remember we talked about this when we are talking about Faraday's law and the likes. So but there's going to be one point that's going to be added, but I'm going to list all the points that you should take when you want to increase the induced current. The first is the coil should rotate faster. Number 2, a stronger magnet should be used. So this point, the coil should rotate faster, is the same as that one which we had said that the movement of the wire must be faster. Then this one, even in the last video we mentioned it, a stronger magnet should be used. The third is the number of turns in the coil should be increased. This one also mentioned it. The last one is the coil should be wound around the soft iron core. So this one in the previous video we did not include it, but here I've included it. So the coil should be wound around a soft iron core, because we know that a soft iron core, it means it's a soft magnetic material, meaning that it is easy to magnetize and easy to demagnetize, resulting in easy to control. So this marks the end of part 3. Hope you have learned a thing or two. Happy solving.